4.5 Rational Functions, Day 1. A rational function is a ratio or a fraction made up of two polynomial functions. Here are two examples: 3x squared plus 5x minus 1 over 2x squared plus 8x plus 7, or something like x squared plus 7x minus 5, or over x plus 2. Now, they could be monomials, numbers, trinomials, binomials, any type of polynomial that is written into a fraction like this. Now, what we're going to be doing with the rational functions is we're really, on this video, is preparing our information so that we are able to graph, which is what we're going to do in day 2. So two of the things that we need to do is find the x and y intercepts. For the x-intercepts, you know how to find those by plugging in y equals 0. And for the y-intercepts, we know how to do that by plugging in x equals 0. So let's do this example. Find the x and y intercepts of the rational function r of x equals x minus 3 over x squared minus x minus 2. For the x-intercepts, if the y value is 0, that means that the whole value of the fraction is equal to 0. And for the whole value of the fraction to equal 0, that means the numerator is going to be equal to 0, the numerator. So if x minus 3 is equal to 0, we solve this and we find out that x is equal to 3. That is our x-intercept. There's only one in this case. Sometimes you might have 2 or 3. For the y-intercepts, that is when you plug in 0 for x. And because when you plug in 0 to a term involving x, it just becomes 0, because no matter what, when you multiply by 0, you get 0. You can just place a 0 for all of the x terms that you have. So here I could write my 0 squared if I want. So 0 minus 3 is negative 3. 0 squared is still 0. Minus 0 minus 2 is negative 2. To simplify that, I get 3 over 2. And so my y-intercept is y equals 3 over 2. Or if I need to change it to a mixed number, it would be 1 and 1/2. Okay? So x and y intercepts are the first step to gathering information for our graph. The next thing are asymptotes. We have vertical asymptotes and horizontal asymptotes. An asymptote, very basically in my own words, is a line containing values that do not qualify as solutions to the function. They act as guidelines to the graph, and the graph of the function gets closer and closer to the asymptote as it approaches infinity. The asymptotes are drawn as dashed lines. Now, the vertical asymptotes are really the lines that are the values that do not qualify as solutions. In fact, they create the rational function to be undefined. The horizontal asymptotes are just more the guidelines. So let's look at vertical asymptotes first. And I'm going to abbreviate that as VA. Vertical asymptotes are when you draw a vertical dashed line, and that is drawn at the value of x that would cause the denominator to be equal to 0. So here I have an example of 5 over x plus 2. Well, when I take the denominator, x plus 2, and set it equal to 0, I would get x equal to negative 2. So what I'm going to do is I'm going to draw a vertical dashed line at negative 2. X equals negative 2. And my graph would look like this, with this red dashed line is showing you the asymptote. Now, a couple things that are going to be important when you actually do the graphing, and it's a good thing to just show you now because we're talking about the asymptote, is that when the graph is approaching the vertical asymptote from the left, we describe that as in two different ways. The first is y is approaching infinity as x is approaching -2, and this little negative up there is saying that we are approaching from the left. So we put a negative to show that it's from the left because on the left side of things we are going towards negative numbers. So a graph of that example would look like this. So if I follow this line going towards the -2 asymptote, you can see my graph starts going to infinity. Okay, and I'm on the left side of that asymptote, which is why I have that negative up in the exponent area of that -2. So as I'm approaching that asymptote, my y values will go to infinity. Okay, now the other option would be to negative infinity, and that graph looks like this. So as y approaches negative infinity, no, not as y approaches, but y does approach negative infinity as x approaches -2 from the left. And I forgot to put a negative here on the -2. Okay, sorry. So y approaches negative infinity as x approaches -2 from the left. So that would be in this green graph. And in the green graph, as I'm approaching from the left side, on the left side, as I'm approaching that -2 asymptote, my y values go down to negative infinity. So those would be the descriptions of those types of graphs. And then on the right-hand side, we would have a positive symbol up in that exponential area. So to show a graph that is y approaches infinity as x approaches -2 from the right is this blue graph here. So now that I'm on the right-hand side of that asymptote, if I follow my graph as I'm approaching that asymptote, my y values go to infinity. Okay? Or I can have this description for the graph that is here in purple. When the y values are approaching negative infinity as x approaches -2 from the right. So again, that little plus sign up there. Okay, so if I follow this, again, I'm on the right-hand side of that asymptote. As I'm approaching that asymptote from the right, my y values go down to negative infinity. So those are the four types of descriptions of a graph. And like I said, we're going to be doing our graphing in day 2, but since we are talking about the asymptotes, it's important to understand the description of the graph at those asymptotes. Here's an example. We want to find the vertical asymptotes for the function t of x equals 2x minus 4 over x squared plus 3x plus 2. Let me get my pen here. Let's do this in blue. And now the vertical asymptotes, as I stated before, is when the denominator is equal to 0. So we need to set the denominator equal to 0. Because it's a quadratic, we need to factor it. X squared plus 3x plus 2. When it is factored, it's x plus 2 times x plus 1. Now you could do um, the product sum rule, diamond method, or some people have a graphing calculator with a program quad 3. So you can enter the values in for A, B, and C into the quad 3 program and get your factors. Now the zeros for these two factors, when you set each one equal to 0, you would get x equal -2, and for x plus 1 equal to 0, you would get x equals -1. And now my vertical asymptotes, I have my lines already kind of created here, just need to be placed in the right spot. I put one vertical asymptote at -1, and then the other vertical asymptote goes to -2, and so I have my vertical asymptotes drawn. And again, right now we're just understanding the different parts of the graph to get started. We're just preparing to graph at the moment. So those are what vertical asymptotes look like. Now, you may be asked to identify the asymptotes by looking at the graph. And by looking at the graph, you need to see that the asymptotes go through the x value of -1 and the x value of -2. And then you would be able to state the equations for those two asymptotes. Same thing with x and y intercepts. If you had to look at a graph that had x and y intercepts, you're looking for those points on the x-axis and the y-axis. Okay, let's go on to vertical asymptotes, or horizontal, sorry. Horizontal asymptotes, or HA, if we are given two polynomials, p of x and k of x, as a rational function, p of x over k of x, there are three possibilities. If I show p of x over k of x as a times x to the n plus whatever and how many other terms we have here, the very first term is what's important here, over b of x to the m plus however many terms. So again, these are the leading coefficients and leading terms of p of x over k of x. Okay? What we're looking at is the degree of the two polynomials, n over m. And if n is greater than m, so the top is bigger than the bottom, the horizontal asymptote is simply y equals 0. Our second possibility is if n and m are equal to each other, the horizontal asymptote is the two leading coefficients written into a fraction, such as a over b. The third possibility, if the n value is greater than m, so the top is greater than the bottom, there are no horizontal asymptotes. So three situations. The top is less than the bottom, so n is less than m, that's y equals 0. When they are equal, we just look at the numbers out in front, the coefficients, and put into a fraction, a over b. And finally, if the top is larger than the bottom, we have no horizontal asymptotes. So let's look at three examples showing these. So here, showing the first example, the numerator value is smaller than the denominator, and I'm looking at, because my my degree of the top is simply 1 over the degree of the bottom is 2. So I know that n is less than m. My horizontal asymptote is y equals 0. Here, they are equal. We have 2 and 2, so n equals m. I look to my coefficients here, 4 over 2, so y equals 4 over 2, which is y equals 2. And that would be my horizontal asymptote. In this third example, my numerator, my n value is greater than my m, so n is greater than m, and because of that, there are no horizontal asymptote. Okay? Now, in this case, there's actually, when the n is one value greater than the m, like we have here, 3 and 2, there's actually a slant asymptote, which we will look on in the day 3 of these videos for 4.5. And that does it for the first day of 4.5.